Okay, let me start with something that sounds, well, frankly, unbelievable. Imagine one of the richest people in the world today. Now, what if I told you that almost all of his money, like nearly 99% of it, was earned after he could start collecting Social Security? You'd probably think, no way, it's impossible. It sounds like some kind of math trick, right? It just doesn't feel logical based on how we experience things day to day. But it's true. It's a documented fact, and we're talking about Warren Buffett, of course. Here's the number that just blows your mind. $81.5 billion dollars of his $84.5 billion net worth came after his 65th birthday. Our brains, they tend to think in straight lines, additive thinking, cause and effect right now. They just aren't really built to handle these kinds of, well, absurd-sounding outcomes. So we focus on his genius stock picks, his credible business sense, which are undeniable, but we miss the biggest driver, the secret ingredient, maybe.
That's exactly it. And that's really the core of what we're digging into today. There's this fundamental mismatch, this gap between how our intuition works and how mathematical growth, especially exponential growth, actually plays out. We're calling this whole idea confounding compounding. Confounding because, well, it confuses us. It trips up our intuition. And compounding because that's the engine exponential growth. So our mission in this deep dive is to explore that gap. We're going to look at some pretty diverse fields, geology.
Okay, let's unpack this then. It sounds like to really grasp the math behind Buffett's billions, we need to take a bit of a scenic route. And you're saying we're starting with ice ages, billion-year-old climate cycles. That seems like the least likely place to look for financial insight. Okay, so why start with geology? It feels a bit out of left field.
Well, it's actually a perfect illustration because, and this is kind of funny, our understanding of our own planet is much younger than you might think. I mean, Isaac Newton was calculating the orbits of planets hundreds of light years away, centuries before scientists really agreed on some basic stuff about Earth's climate history.
Really, like the idea of ice ages.
Exactly.
Yeah.
For a long time, the idea that huge chunks of the Earth were once covered in ice just seemed preposterous. It wasn't until maybe the mid-1800s that the scientific community finally came around. And it was because the physical evidence was just, well, everywhere and undeniable once they started looking.
What kind of evidence are we talking about?
Oh, things like giant boulders. Geologists call them erratic boulders, just sitting in landscapes where they clearly didn't belong geologically. Like, imagine a massive granite boulder in the middle of a limestone field.
Yeah.
Something huge had to move it there.
Ah, glaciers.
Glaciers, exactly. And also huge areas of bedrock scraped and grooved, these long scratches called glacial striations. They're like the planet's stretch marks, showing where massive ice sheets had moved.
Okay, so they realized there was an ice age, but you said cycles.
Right, that was the next big puzzle.
Uh-huh.
The evidence didn't point to just one deep freeze. It showed at least 5 distinct, measurable cycles of glaciation and thawing over Earth's history.
5 times, the whole planet freezing over and melting back. The amount of energy involved in that, I mean, it must have required some colossal force, right? Some massive sudden change.
That's precisely what the early theories assumed. They needed a cause as big as the effect. So the ideas were suitably grand. One popular theory was like the sudden catastrophic uplift of entire mountain ranges. The idea was that this would drastically change wind patterns, ocean currents, and plunge the Earth into cold.
Okay, that sounds suitably massive.
Another idea was that maybe Earth's natural state was ice, and it was only interrupted occasionally by, say, enormous volcanic eruptions that pumped enough greenhouse gases into the atmosphere to warm things up for a while before it inevitably slipped back into the ice.
Big events for a big outcome. Makes sense. But you mentioned earlier these big theories didn't quite work.
They didn't. Because, well, think about it. A huge volcanic eruption or the rise of a mountain range that might explain one ice age? Maybe. But it couldn't explain the pattern, the repetition, the seemingly regular rhythm of these 5 distinct cycles found in the geological record. The massive one-off catalyst just didn't fit the cyclical evidence.
So the answer wasn't a big hammer blow, it was something else.
It was something much more subtle. And this brings us to the early 1900s and a Serbian scientist named Milutin Milankovic.
Okay.
Milankovic basically ignored the catastrophic theories and went back to basics, orbital mechanics. He started looking at the very gentle, very slow gravitational tugs from the sun, the moon, even other planets like Jupiter.
How could that freeze the Earth? Those forces sound tiny.
They are tiny in the short term. But Milankovic figured out that over very long timescales, tens of thousands, hundreds of thousands of years, these gentle pulls subtly change Earth's orbit and the tilt of its axis. And these tiny changes gradually alter the amount of solar radiation, the sunlight, hitting different parts of the Earth at different times of the year.
Can you break that down a bit, the Milankovitch cycles?
Sure. There are three main components. First, there's eccentricity. That's just the shape of Earth's orbit around the sun. It goes from being more circular to slightly more elliptical, like an oval, and back again over about 100,000 years. Second is obliquity. That's the tilt of Earth's axis. The reason we have seasons. That tilt actually nods back and forth by a couple of degrees over about 41,000 years. A bigger tilt means more extreme seasons.
Right.
And third is precession. Imagine the Earth spinning like a top. It sort of wobbles slightly. That wobble changes which hemisphere is pointed towards the sun during different parts of the orbit, and it cycles around every 23,000 years or so. None of these changes are big enough for us to notice in our lifetimes, but they create these long, slow, predictable variations in sunlight distribution.
Wow. Okay, so incredibly slow, incredibly gentle inputs, but that still doesn't quite explain the sudden freezing, does it?
Not entirely. That's where the next piece comes in, from a Russian meteorologist, Vladimir Kupin. He took Milankovich's orbital cycles and connected them to the actual climate mechanism. And what Kupin found was the really counterintuitive part, the absolute key. It wasn't unusually cold winters that triggered an ice age.
No.
No, it was moderately cool summers. Summers that just weren't quite warm enough.
Cool summers. How does that cause an ice age? That seems backward.
It does. But think about the compounding effect. It all comes down to whether the snow from the previous winter melts completely. Imagine a summer that's just a little bit cooler than average. Not freezing, just cool. Maybe some of the snow that fell the previous winter doesn't melt entirely, especially at higher latitudes or altitudes.
Okay, so you have a little leftover snow.
Exactly. Just a small patch, a thin layer maybe. But that leftover snow is now the base for next winter's snowfall. It makes it easier for snow to accumulate because the ground is already insulated and reflective. And critically, that slightly thicker snowpack has a better chance of surviving the next summer, even if it's just averagely cool.
Ah, I see. So the leftover snow makes it easier for more snow to stick around the next year.
Precisely. It's a positive feedback loop. A snowball effect, literally. That persistent snow cover reflects more sunlight back into space. Snow is much more reflective than dark ground or water, right? That's called albedo.
Right, higher albedo.
So more reflected sunlight means slightly less warming, which means even cooler local temperatures, which means more snow survives the summer, which increases the reflective area, and on it goes. That tiny initial condition, a summer just cool enough to not melt everything, compounds itself. Over centuries, which is just a blink in geological time, that little patch of persistent snow grows into a massive continental ice sheet, miles thick.
Wow. That's actually incredible. It flips the whole idea of needing a giant cause on its head.
It really does. There's a great quote from a glaciologist, Wen Schultz, that sums it up perfectly. It is not necessarily the amount of snow that causes ice sheets, but the fact that snow, however little, lasts. Persistence.
Okay, so the huge takeaway from the ice ages isn't about massive force.
No. It's that you don't need tremendous force to get tremendous results. You just need a small positive change, like a slightly cooler summer, that can fuel future growth and, crucially, last long enough for compounding to work its magic. The persistence of that tiny advantage is what eventually creates the world-altering outcome.
That ice age example makes it seem so logical in hindsight. A small thing, persisting, creates a huge result. Yet when we look at finance or technology or even our own careers, we seem to just ignore this principle. Why is it so hard to grasp if the math is simple?
Yeah, it's a great question. It really boils down to how our brains evolved, our cognitive biases. Linear thinking is just much more intuitive for us. Think about it from an evolutionary standpoint. For almost all of human history, understanding simple addition, if I add 3 rocks to these 5 rocks, I have 8 rocks, or basic linear cause and effect was way more important for survival than understanding exponential growth.
Like that mental math example you mentioned earlier.
Exactly. If I ask you what's 8 plus 8 plus 8, 9 times, you can probably do that in your head reasonably quickly. It's 72. It feels manageable, linear.
Right.
But if I ask what's 8 times 8 times 8, 9 times, your head just explodes, right? The answer is, 134 million and change? The sheer scale of multiplicative growth versus additive growth is something we just can't intuitively feel.
And that surprise factor. I mean, I know people who've said seeing a compound interest chart for the first time, maybe showing savings from age 20 versus age 30, genuinely felt like a life-changing moment. It shocked them.
It does. And it's probably not that the math itself changed their life, but the realization did, the surprise. It's because the result, especially those later years on the chart where the curve goes almost vertical, just doesn't feel right based on our everyday linear experience. It looks like magic, even though it's just math.
So Okay, if it's so counterintuitive, what's the danger? We just underestimate things.
It's more than just underestimating. It actively shapes our behavior, often in unhelpful ways. Because compounding feels weird, even the smartest people can overlook its power. The real danger is that we then focus all our energy on trying to solve problems or achieve goals through other means, usually by looking for those big one-off events, the financial equivalent of the giant volcanic eruption theory for ice ages.
Like trying to hit a home run stock pick or
Yeah.
land one massive deal.
Exactly. We chase the big, immediate payout, the high return this year, even if it's risky and can't be repeated. We're drawn to the drama of the big win. We put all our effort into trying to force a huge result quickly, rather than focusing on the moderately cool summer approach, finding a small, sustainable, positive rate of return or improvement that we can simply stick with for a very, very long time. We miss the power of just letting the process work because it's slow and, frankly, kind of boring.
Patience isn't sexy, I guess.
Not at all. But as we'll see, it's incredibly powerful.
Okay, let's loop back to Warren Buffett then, and that staggering statistic, 99% of his wealth after age 65. Applying that Ice Age lesson, it suggests we're focusing too much on his investing skill, his brilliance.
I think that's largely true. Look, nobody disputes Buffett is a brilliant investor. He's achieved something like 22% average annual returns over his career, which is phenomenal, truly exceptional. But focusing only on that 22% misses the bigger picture. The really crucial variable isn't just the rate of return, it's the duration. He hasn't just been a phenomenal investor. He's been a phenomenal investor for, what is it now, the 3/4 of a century. He started investing seriously as a kid.
The source material had a really effective thought experiment on this, didn't it? Highlighting the time factor. Buffett started young, had about $9.3 million, inflation adjusted, by age 30.
Right. Now, let's imagine a slightly different path for him. Let's say he did what most people do, maybe traveled, explored different careers in his 20s, found himself. And let's say he only started getting serious about investing around age 30. And at that point, he had a more typical, maybe $25,000 net worth. Still respectable, but vastly different from his actual start. Now, crucially, in this alternate reality, let's assume he still has the exact same investing genius. He still earns that amazing 22% annual return. But instead of working into his 90s, he decides to retire at age 60, go play golf, enjoy life. A pretty standard retirement age.
Okay, so same genius, same 22% return, but he starts later with less and stops 30 years earlier. What happens to his net worth in that scenario?
Well, instead of the $84.5 billion he actually has, his net worth today in that scenario would be around $11.9 million.
Wow, from $84.5 billion down to $11.9 million, just by changing the start and end dates.
Just by changing the time window. It's a 99.9% difference. It's almost unbelievable, but the math is relentless. What it tells you is that effectively all of Buffett's financial success is tied not just to his skill during his peak earning years, but critically to the base he built when he was basically a teenager and the longevity he maintained deep into his geriatric years. His skill is investing, yes, but his secret weapon, the multiplier, is time.
Okay, but hang on. I can hear the counter-argument already. Someone might say, sure, time is important, but you still need the skill, right? If Buffett had just earned average market returns, like 8% or 10%, for 75 years, he wouldn't be Warren Buffett. You need the skill to make the time valuable.
That's a really fair point, and it's important. Yes, of course, the skill matters. You need good returns over that long period. You can't compound mediocrity into billions, usually. But here's the nuance. Extreme longevity reduces the requirement for extreme skill. Time becomes a substitute for a higher return rate, in a way. Think about it. Would you rather have a 25% annual return for 10 years or an 8% return for 50 years? The 8% over the longer period wins, and it's not even close. Buffett's genius wasn't just picking stocks, it was finding a strategy that produced good enough returns and, crucially, was repeatable and durable enough that he could stick with it psychologically and practically for 75 years without blowing up or giving up. His strategy was built for the long haul.
That makes sense. It wasn't just high returns, it was sustainable returns. The Jim Simons comparison in the source really drives this home, doesn't it? Pitting extreme returns against extreme time.
Oh, absolutely. Jim Simons is fascinating. He runs Renaissance Technologies, a hedge fund famous for its quantitative algorithmic approach. Simons himself is a brilliant mathematician, and his flagship Medallion Fund has generated returns that are just legendary, about 66% annually on average since 1988. That's 3 times Buffett's already incredible, 22% average.
Okay, 3 times the annual return. Our linear brain immediately thinks he must be 3 times richer, or probably way more, right?
Yeah, you'd think so. But again, our intuition fails us spectacularly when compounding is involved. Simon's net worth is estimated around $21 billion, which is staggering wealth by any normal measure, but it's still about 75% less than Warren Buffett's.
Despite a return rate 3 times higher, how?
Time. It's always time. Simons was a successful mathematician first. He didn't really hit his stride in finance and launch Renaissance until he was 50 years old. So he's had less than half as many years for that incredible 66% return to compound compared to Buffett's 75-year runway. The difference in their wealth isn't primarily about the return rate, it's about the duration. Simon started later.
And just to hammer home the sheer mathematical power here, the source did a theoretical calculation. What if Simons had started earlier? What if he'd managed that 66% return for the same 70-odd years Buffett has been investing?
Yeah, the number becomes completely meaningless in practical terms. It's just an illustration of exponential growth gone wild. If Simons had earned 66% a year for 70 years, his theoretical net worth would be something like 63 quintillion, 900 quadrillion, 781 trillion. I mean, it's a number with 21 digits after the first one. It's more money than exists on the planet by orders of magnitude.
Left. Okay, yeah, that's definitely just a math exercise at that point, but it makes the point.
It really does. It shows how variations in the time assumption lead to these almost infinitely different outcomes, far more so than reasonable variations in the return rate assumption over shorter periods.
So when we think about learning from Buffett, maybe the thousands of books dissecting his value investing techniques are not wrong, but perhaps missing the most important lesson.
I think they often miss the forest for the trees. The most critical book about Buffett probably shouldn't be about how he analyzes balance sheets. It should be titled something like, "This guy has been investing consistently for 3/4 of a century." We're so desperate to find the secret hack, the complex strategy, the alpha, that we overlook the simplest, most powerful factor, just sticking with a reasonable plan for an incredibly long time. Maybe the best economics book ever written would just be titled "Shut Up and Wait." And inside, it would just have one chart showing long-term economic growth, just to illustrate the power of staying invested.
The boring patient strategy. It's the hardest thing to sell, isn't it? And maybe the easiest thing to dismiss, right? And this isn't just ancient history like ice ages or, legends like Buffett. This blindness to compounding happens right now, especially with technology, doesn't it? The hard drive example seems perfect here.
Oh, absolutely. Data storage growth is a fantastic, very tangible example of exponential growth, just completely defying prediction in recent memory. If you track it, it starts slow, almost painfully slow by today's standards.
Yeah.
Back in the 1950s, you had the IBM RAM-ACK drive, stored maybe 3.5 megabytes, and it's the size of like 2 refrigerators. Huge thing.
Okay.
Fast forward to the 1970s, IBM's Winchester drive gets you up to maybe 70 megabytes.
Yeah.
Then into the early 1990s, a typical PC might have had, 200, maybe 500 megabytes?
So that's 40 years, 1950s to 1990s, of pretty slow, steady, almost linear-looking progress. You go from 3.5 megs to maybe 300 megs average. Seems manageable.
Exactly. It sets expectations. You mentally draw a line based on that progress, and then the curve goes vertical. The compounding kicks in. Suddenly, around 1999, Apple ships the iMac with a 6-gigabyte drive. That's thousands of megabytes. Just a few years later, 2003, you're seeing 120-gigabyte drives as standard. Then it just keeps accelerating. By 2011, you see the first 4-terabyte drives. That's 4,000 gigabytes. Now, we're routinely talking about drives measured in tens of terabytes, 60 TB, even 100 TB drives introduced around 2019.
Let's just pause on those numbers. Phase 1, 1950 to 1990, 40 years. We gain maybe, let's round it up, 300 megabytes of storage capacity.
Right. Phase 2, 1990 to roughly today, about 30 years, we gain 100 million megabytes, give or take, going up to that 100 TB level.
That's insane. The growth in the last few years completely dwarfs the growth of the first 40 years.
By factors of thousands or millions. That's the compounding curve hitting its stride. The gains in each period become fueled by the base created in the previous period, and it just explodes upwards.
And this explains why even the experts get it wrong. If you were a smart technologist back in the 50s or 60s looking at that early progress...
Yeah, maybe you'd be optimistic. Maybe you'd predict storage getting 1,000 times bigger in your lifetime. If you were really bullish, maybe 10,000 times bigger. That would have sounded incredibly bold back then.
But nobody says.
Nobody says, oh yeah, within my lifetime, storage capacity will increase by 30 million times. Sounds utterly ridiculous, but that's roughly what happened. The exponential reality outpaced even the most optimistic linear or slightly curved projection.
And even people right at the cutting edge can get caught thinking in the old way. The Bill Gates anecdote about Gmail is pretty telling.
Yeah, that was back in 2004. Google launches Gmail, and the big selling point was offering a full gigabyte of free storage per user. which at the time seemed enormous.
Mhm.
And Bill Gates, who was obviously deep in the tech world, publicly sort of questioned it. Like, why would anyone need a whole gigabyte just for email? Microsoft's own Hotmail offered much less.
Right, I remember that.
And Stephen Levy, the tech writer, made a great observation about it. He said Gates' thinking seemed anchored in the old paradigm of storage being a commodity that must be conserved. Even Gates, arguably one of the architects of the digital age, was still mentally stuck on the slower part of the curve, thinking linearly about scarcity, just as the technology was entering the phase of exponential abundance. It shows how hard it is to intuitively adjust to that acceleration, even when you're helping to drive it.
So this applies across the board in tech, right? Processing power with Moore's law, network effects with Metcalfe's law. It's the same pattern. Slow start, looks linear, then suddenly, whoosh.
Exactly the same pattern. And the cognitive bias, the failure to truly internalize the implications of that whoosh, is the same too.
So how do we bring this back to, practical advice? If our brains are bad at this, what should we actually do?
Well, the first step is just recognizing the bias. Understanding why compounding feels weird helps you consciously override that intuition. And it means shifting your focus. Instead of chasing the big, sudden win, the equivalent of trying to invent the 100 TB drive overnight, you focus on the moderately cool summer. You look for the small, positive, sustainable edge or improvement that you can maintain consistently over time.
Give me an example, like in a career.
Okay, so in a career, maybe the big catalyst thinking is trying to get a massive promotion or 50% raise by job hopping constantly. High impact if it works, but risky, maybe burns bridges, hard to sustain. The moderately cool summer approach might be committing to learn one new practical skill relevant to your field every single year. Just one. It's small, manageable, but that skill doesn't melt away. It adds to your base. Next year, you add another. After 10, 15, 20 years, that consistent layering of small skills compounds into a deep, unique expertise that makes you incredibly valuable. The cumulative effect is way bigger than any single promotion you might have chased early on.
So, wrapping it all together, this difficulty we have with compounding, this bias towards the Big Bang, it's responsible for a lot of failure.
I think it's responsible for a huge amount of disappointment, yeah. Disappointing trades in the market, bad business strategies, failed attempts to get rich quick. People pour all their effort, mental energy, financial capital into trying to get the absolute highest return possible right now because that feels like the fastest path. They're optimizing for the wrong variable.
Because the highest returns often aren't sustainable. Like that 66% Simons achieved amazing, but maybe not replicable for 70 years.
Exactly. Good investing, like building an ice sheet apparently, isn't about the most intense burst of energy. It's not about earning the absolute highest returns, because those often involve huge risks, or they're one-offs you can't repeat, or they rely on conditions that won't last. It's about earning pretty good returns that you can stick with and which can be repeated for the longest period of time. That's the magic formula. Pretty good, repeatable, and durable. That's when compounding truly gets unleashed. Hashtag tag outro.
Wow. Okay, so that was quite the journey. We started with this almost unbelievable fact about Warren Buffett, 99% of his wealth coming after retirement age, and we traced that same mathematical engine, that compounding power, back through, of all things, the formation of massive ice sheets driven by just slightly cool summers, allowing snow to persist. We saw how our own brains fight against understanding this, whether we're trying to multiply numbers in our head or predict the future of technology like hard drives.
And the thread connecting it all seems to be this. When we look for the cause of really big transformative results, geological, financial, technological hunts, our instinct is to find an equally big, sudden cause, a massive force of brilliant insight, a single breakthrough moment. But the real answer, so often, seems to lie in something much less dramatic. Time, patience, consistency, the ability to just maintain a small advantage, a small positive rate of growth, and let it keep building on itself year after year, decade after decade, letting the base survive and grow.
So maybe the final thought for everyone listening. If we know we're psychologically wired to underestimate this power, to look for the big hit instead of the slow build, it's worth asking yourself, isn't it? Where else in your life, maybe your career, maybe learning a skill, maybe even just building your knowledge, are you focusing all your energy on finding that massive catalyst, that one big break, when the real, more reliable path to an extraordinary result might just be that small, consistent layer of effort that simply lasts?
Yeah, that persistence is the engine. And the time, the longevity is the fuel. Shifting your focus from chasing the highest peak to simply ensuring steady, durable progress. That might be the most profound change you can make. Because the flip side, chasing those spectacular but fleeting gains, the ones you can't hold on to, well, history is full of tragic stories that start that way. Definitely something to think about.